And then you also want to record.
Okay, let's go back to Zoom. Record to the cloud. Share screen.
And then you also want to record.
Okay, let's go back to Zoom.
Okay, you now need to,
Record
in your
cloud.
browser, you need to mute.
Share screen.
And then you also want to record. You gotta mute
Okay,
this
let's go
one.
back to Zoom.
Okay, you now need to,
Record
in your browser, you need
Why
to
do I not
mute.
have this showing up here?
And then you also want to, you want to go and mute the YouTube.
Go back to Zoom.
Okay, you now need to,
Don't
need to mute it.
Why do I not have this showing up here? That's better.
You want to go and mute the YouTube. Okay, you now need to, okay, now you're good. This access. Oh yeah, I've got it. Like you're like the mobile one today. I'm gonna stay with the,
Yeah,
this
I'm
one.
gonna dominate. So I'm gonna do the first half testing.
Nice.
Um,
Hmm?
The Zoom link, because I didn't have it on record. I have the other two ones.
Oh, that's one.
If Lyle could just copy it from the Zoom link I was currently using. That's you're in the personal conversation.
oh, where's the darn? I don't know where. Mm. Nope, that's not good. Trying to find my thing here now. Ha. Now we're good. Oh, okay. Technology rules, maybe. Oh, I didn't bring my advancer. Okay. Remote people, do we have sound? Okay, we good to start? Pretty good. Hello, live audience. So nice to see people here. Good. Cool. So, time series this week. We'll talk a bit about some of the things we're doing. Coming next week are Transformers. We're exciting. Not the Hasbro Transformers, but Bert and Clip and GPT-3, which we'll do last time. First of all, you should all have gotten feedback on your projects. If you didn't, Slack us, edu us, email us, whatever. Secondly, we're trying to get AWS credit to give you more GPU power, we hope. And then next week, our projects. Any bureaucratic questions, any announcements? Everybody's good. Cool. So let's see if I can make this thing get out of the way. Yes. This is not working. This should. Oh, that's not good. This is supposed to feed through here. Okay. Technology sucks.
It could be a video issue. Okay, keep going.
Okay, I'll keep going and
see if
I will stay here for now. Cool. So this week is time series. And there's a bunch of different ways to look at it. I want to sort of quickly review them and then ask you about them, to think about them. And the idea with time series is we have a sequence of observations. I think the observation being a word, I'm a language guy, but they could be a sequence of images, like a video, or a sequence of measurements of a power plant or anything. And the general model is to take the observation, like the word, map it to an embedding. The fancy word is a context oblivious embedding, because it doesn't depend upon the words before or after. Or for the image, take the pixels, map the pixels to an embedding using a standard piece, and then learn something like, for example, a recurrent neural net for this week, right? And the idea of each of these is that at each point you have a neural net which takes in two inputs. It takes in the current embedding of the current word or image, and it takes in the previous output of the neural net, the state, right? So it takes in the embedding of the word two, and it takes in the hidden state from before, and it runs it through whatever you want, a bunch of ReLUs, and gives an output. And then at each time you train it by predicting what the next word will be. Supervised, unsupervised? Unsupervised? Do we have labels? So maybe there's unsupervised, there's no Y's, or maybe it is supervised. You consider the next word the label, right? And there's a fancy word for this kind of supervision. Self-supervised, right? So standard in time series is to use self-supervised learning. It's not unsupervised. Lots of self-supervised data. Who knows?
Apparently we've got to stay close to this. I don't know which microphone it is.
Cool. So questions, and this model is now called a language model. It's a mapping from an arbitrary sequence of words to a probability distribution over the next word. Good? Great. Okay. So we got basically three uses, which I'm going to go through and remind you. They're in the, I've stolen the slides from the worksheet. Word tagging, sentence labeling, and generative modeling. In word tagging, we're going to take each sequence of words and then, whoa, no, come in here. I'm just trying. Hate technology. Yes. No, go away. Sequence of words. Really doesn't love me. I want this to go away. Yeah, maybe I can move it to the left side. There we go. Now at least it's smaller. Okay. So we're going to take each word. We're going to embed the word with a context oblivious embedding, right? A word to vector mapping. We'll feed it to the neural net. We will then take the other piece. We'll get a new output, which is what we usually call, what do we call the output of a neural net inside like a hidden Markov model or a Kalman filter? It's a state estimate, right? The state estimate, the output of the neural net after I've seen I went to, the output here is a vector that describes, that sums up everything we know about the past that's likely to be useful for predicting the future. And that assumption to make that work is the, someone from 520, who's the Russian dude? Markov, yes, right? The Markov assumption, right? We assume the world's Markovian in a recurrent net, that once we have a vector here, the past will tell me nothing more about the future. This gives us a different kind of embedding. Note there's two different embeddings here. One is the embedding of a word like went or to or I, that maps from a word to an embedding. The other embedding maps from all of the past to something that summarizes the past. Right? So that's embedding not just of two, but of the whole history. That embedding is called a state or a context sensitive embedding, because it depends upon the context. In this case, the left context. Make sense? Now we can take that state vector and run it through a neural net and predict a label. Note this is a semi-supervised learning, right? Lots of self-supervision to learn the mapping from a sequence of words to a state, and then a small amount of labels from state to, is it a preposition? Is it a verb? Is it a pronoun? Is it a conjunction? Good. You can also take a whole, oh wait, before I leave that, this is all left to right. If you're actually doing something like, say, speech recognition, you mostly want to go left to right. You take the past up the current thing, take the speech, and then produce the words, the characters that show up on your screen. But for, say, labeling parts of the speech, you might want to use the right context as well as the left. How would you do that? Bidirectional, right? You have the exact same thing. Instead of running in addition to running an RNN from left to right, past to future, you run a second RNN from future to past. Right? Mathematically exactly equivalent, assuming, of course, that you know the future. Works great for books or Wikipedia, doesn't work so well for live speech. You can also take a whole sequence and take the state at the end of it, and then use that and label the whole sentence. What's the topic of the sentence? And one can also take the whole sentence embedding and feed that into a second neural net. So the first neural net, called the encoder, takes in a sequence of words and produces a vector, right, that best summarizes that sequence of words. Then we feed that into a second neural net, which is trained to produce words, and it then goes and, for example, translates them. Which is not how current translation works. We'll come in a second to why that is. But for a while, these were used. And they may be used again. There's a lot of argument right now in NLP as to, will transformers be the right thing for all future, or will recurrent nets come back again? Questions? Okay, I'm going to start asking questions. Okay, so let's think of a bunch of problems. The simplest one, we got a big image, and we want to look to find a dog or a computer or something in it. Right? Ask the question, is there a dog in this image? If so, where? How would you code that up? What architecture do you use? Pardon? CNN is the obvious way to do it. So how does the CNN search through an image? Oh, it goes sequentially. Does the CNN really go sequentially? This is going to really matter as a computer scientist because these things are computationally really expensive. So sequentially, in the sense you have a whole bunch of filters at different locations. But let me ask again, does the computer compute sequentially? It's parallel. You can do the whole thing executed in parallel. You can take all of those images, all those little filters all at once and slam them in. And we did some calculations earlier when we did CNNs that said, hey, you want to have enough memory on your GPU chip to do them all at once. Does that make sense? So sequential is probably the wrong word there. Does that make sense? Yeah. The same filters applied over lots of locations, right? So conceptually, you can imagine moving the filter across the image, here, and doing each of them one after the other. In practice on modern deep learning, it does all of them at the same time. Why is it so important to do them at the same time rather than sequentially? Faster. right? If you're going to check 100 different subfilters, it's ballpark 100 times faster to do them all at once than to do them one after the other. And a factor of 100 starts to really matter for these things, right? They're slow. Does that make sense? So mostly in CNNs, it's run in parallel. You have a bunch of windows. If one object could be big and one could be small, it could be a small dog or a big dog. How do you find a small dog or a big dog in an image? What assumption do you make when you design the neural net? The size of the, well, the size is invariant. You have to put in filters of different sizes. Could be a 5 by 5, could be a 9 by 9 filter, right? So you're sort of assuming what size they might be. Now, say you wanted to find a dog in a video. I'm going to stream a video, and we're going to have lots of images. Thousands, millions of images. Hey, videos can be long. How are you going to find a dog in a, or all the dogs in a video? No. Look in each image one by one, maybe. Maybe. Is there a way you might get more information than looking at each video clip one by one? Take a timestamp with a snapshot of the video, sorry.
So, I mean, don't take a snapshot of the video every millisecond, or we do it after.
So instead of sampling continuously, you could actually sample periodically. Yeah. So maybe the motion matters. Maybe it's not just the image. Can you recognize a person from behind by their gait? Mostly yes, actually. People have, and dogs have dogs compared to people, fairly characteristic gaits or motions. So maybe for video, you don't want to look at a single video. You want to look at a sequence of images. Look at changes in them. Maybe the dog is partly there and then partly vanishes and partly shows up again. And you never see a whole dog in one image, but you see a little slice of a dog as it goes by through the window. So there's lots of reasons you might want to have a longer stretch. Can I put the whole video in at once? The same way I put a whole image in at once. Not going to work, right? Videos are too long, yeah? And what does it say?
Find frames with lots of changes with respect to time. And if there's lots of changes in the frame, then run an object detection on that particular frame.
So identify frames with lots of changes, and then look for the ones that have lots of changes. Makes sense as long as the dogs are moving, means you're not going to see a fixed dog. Are people better at recognizing moving dogs or fixed dogs? If I show you a still image, where's Waldo? Or an image with Waldo or the dog moving in it? Usually easy to identify things that are changing. You can see the dog moving from it. Your eye is drawn to things that change. So it's often a good idea. You'll miss that sleeping dog in the corner. So if you've got a sequence, you're not going to be able to do the whole thing all at once. You're going to have to do something that either, well, what are the two alternatives for architectures? I want to recognize a dog, a moving dog in a video in a deep learning style. I don't want too much pre-processing and feature recognition and finding where that's moving. I just want to put the video into my deep learning thing. What kind of architecture could I use? What's the input, right? I need an X going in and the output being dog, no dog. I know the remote people can't see this, but image time one, image, 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 image. Got a whole bunch of these. 10,000 images. Some of them have dogs in them. Yeah.
Wait, how about suggested RNN?
An RNN is one way to do it, right? So the recurrent neural net says, hey, each of these images, I send an embedding of that image in. I then have a sequence here. I use a recurrent neural net. Makes sense. So RNN is the obvious thing to do. What else might I do instead? What would you have done before RNN? Yep. CNN. How do I do a CNN with I can take my CNN, be an input, which is a tensor. It's X by Y by RGB by the number of items in my window. What's better, an RNN or a CNN? Oh, anybody who's taken a 520 with me always knows the answer. Depends. It depends, right? Right? So that's what I just said. Let's try and look at the costs of the computations. And the one question is, what's your sequence length? How many images do you have? Right, so you got n images. And in a recurrent neural net, you're going to have to do n things sequentially. First image, second image, up to nth image. That requires a whole bunch of things one after the other. Because to predict the n minus first image, you got to do n minus second, n minus third, n minus fourth, all the way back to 1. That's an order n sequential operation. One after the other. This is the reason that people in my world, which is NLP, don't use recurrent neural nets anymore. They don't want to do n things after each other. They want to do it all at once, right? A convolutional neural net, the whole thing goes in here, boom. No recurrence. Sequential operation, 1. Cool, but we're in computer science, no free lunch. What's the complexity per layer, right? And if I have a representation that's of size D, my embedding of my image or my word is size D, right? Might be a 300-dimensional embedding or a 600-dimensional embedding of my word or image there. Then a recurrent neural net is going to take something that requires n times D squared, complexity per layer. The convolution network depends upon the kernel size, sort of the K. How big this is going to take more like K times n times D squared. So convolutional requires more memory per layer, per time, but no unwinding over time. Does that make sense? You can be parallel, it can be sequential. No free lunch. In the current computing world, what do people mostly do? Parallel or sequential? The parallel is winning at the moment, right? If you've got enough memory on your GPU, then you run something more like a convolutional neural net or a transformer, which we'll cover next week, which is in fact a autoencoder that works in parallel, not sequentially. So transformers are replacing currently at places like Google and Baidu, Facebook, and they came in NLP now and also in Vision. They're replacing the recurrence because it's faster. You can do it in parallel. Difference? If you're doing recurrent neural net, what's you have to pick in terms of how much history you keep? Nothing. Recurrence goes back forever, right? Whereas for a CNN, you're going to have to pick a window. How big a window do I care about? Cool. Okay. Here's a different time series. This is an EEG. Yes, question, please. As an input for the CNN, what we're putting in is all of the word embeddings or all of the image embeddings within the window in one big input. You learn for the whole length of the video. Well, each window, you're going to either predict what comes next for your language model. So that's the next word, the next embedding based on the preceding ones, or you're going to predict some sort of a label. So as you have a CNN for a time series, at each time point, you have a window's worth of history, K preceding ones, and then so you predict the next word. Make sense? And you do that over and over again, but at each point, it's one shot. Boom, in goes the last K words, out comes the next word. Repeat that each time. So there is no sequential in the sense of having to, I can't estimate this output until I know the one before it, which tries one before it, tries one before it. This can't be parallelized. Right? A sequential one, if you have to actually compute going forward, you got to do this, then this, then this, then this, then this. In a real sequential time series, like a hidden Markov model or a Kalman filter, there's no way to predict one shot. It requires sequentially multiplying each time. Does that make sense? Very important point. And one that it's worth covering both recurrent neural nets and transformers, because depending on the decade and the architecture, one is better or worse. Right? There is no one that uniformly dominates. All of that said, transformers are coming increasingly to win right now. Good. Good. Okay, EEG. You want to find a seizure. This is what a seizure looks like, I'm told. Time series, bunch of paths. What sort of a model do I want? CNN, RNN. Yes, Conrad hasn't seen this one. You can play too.
I can play.
You can play too, yeah.
Oh, nice.
You want to use a CNN or an RNN?
Well, I don't know. I mean, like.
How would you decide? That's the perfect question.
Yeah, so stuff happens at some point of time.
Like a long sequence.
There's a really long sequence. No,
I
I worked a little on that. So we have like basically forever going on, nothing happening, and then stuff is different. What would that mean?
Or something else.
Let's say a CNN, because we're just looking for that one spot where there's all that activity. So we're not looking all the way back to the beginning.
Okay, so CNN, here, above you again. CNN, because you're looking for a spot where it happens, the long history doesn't matter. Yep.
And Kata also votes for CNNs because he says it's easy to apply a filter on the sequence of ECG data.
Yeah, we got 2 votes for CNN. And in fact, the winner is CNN.
CNN, what a surprise.
There we go.
But
Okay.
I want to say it might slightly depend on how you want to ask that question, because there's some people that believe that before you have a seizure, some things just so very slightly change so that they could tell people who have seizures like hours ahead of time, like, it's not a good day. You should do something differently today. So if we take that view, then a CNN sounds like the wrong idea. We want to like see that something subtly changes ahead of time.
I might want an RNN, or I might want to do something I've been playing with, using a CNN with a short time window, and then something that summarizes the data and averages it and gives features over the much longer period.
Yeah,
But I agree. Often you want to know what's happening the preceding 2 days. And the real thing is not to tell when you have a seizure, which is obvious. I'd like to know the day before.
but like that strategy that Lyle just sketched, I think is very important. Like in the context of CNN, if we want to like basically build back in this long time scale, the way we can do it is by having an idea into the domain and what are the features we want to use. So that then highlights when we'd want to use like this strategy versus say an RNN strategy. If we are totally clueless what the right features are, what's our choice? Not like, we don't know how to summarize the past, and RNNs can basically learn how to summarize the past.
And lots of the projects, people say, how do I do something innovative? And I think innovative almost always means understanding something about your world. And it turns out that if you want to do a project on EEGs and you have no idea about them, it's really hard to be innovative because you don't actually understand the time scales on which things happen and the different questions you might ask. And if you do a Kaggle competition to recognize the EEG when the seizure was happening, you're missing the stuff that's actually interesting. These guys are like 98 point something% accurate. The problem is boring. But will I have a seizure tomorrow? That one's still open.
That's an open question, and it's highly relevant. Brian Litt here is doing that exactly.
Yeah, we have
Can
some
we-
people in this group who are
Yeah,
class or in his lab.
yeah, and they basically want to know, can we put a stimulation into the brain to stop the episode before it's happening? So they would really very much like some code that tells them what's going to happen.
Yeah. Cool. You're good. Okay. Looking forward to our next week. You want to answer a question on a Wikipedia page. What year was Benjamin Franklin born? Question, long page. Someone? We need some sort of attention, right? That's going to be the big piece here. So let's sort of review what attention looks like, which is sort of the biggest, hardest concept, I think, in all of NLP. So what do we have? We have a sequence of words. Here we have French, montarté. Each word is, yeah, Conrad likes that one. His French is good.
It's yeah.
We'll get there. So you embed each word with a vector, you give it to an RNN, you have an encoder. You want to then, for the sequence have a decoder that takes each of these words and takes the embedding and says, he hit me with a, and predict the next word. But for a long sentence, you'd like to not remember the last whole book by Camus. You want to actually, as you go along, translate. Make sense? So when I predict the next word, I want to both take in the current embedding of where I am so far in my output and all of the potential words here to see which of these words are most relevant. And mostly there are a bunch of ways, and they're in the worksheet, of finding similarity or attention, but you can think of taking a dot product. How similar is the embedding of entarté to the embedding of the sentence up to here? How similar is the word il embedding to the embedding of the sentence? And what you'll find is that, particularly in English and French, that are sort of similar in their alignment, often the last word is most important.
And I just want to emphasize the cool property of French, that hit with the pi is a single word in French.
Yes, there's not a one-to-one mapping. Most people in this audience are multilingual. They know that one word in English may be 2 or 3 words in Hindi or Chinese, or maybe vice versa, right? So
yeah,
yes.
but hitting with the pi as a word, that's something
I
about
know,
priorities.
We're missing in English. I know, it's terrible. Why is there no word in English for in pieing?
That's right.
Pie facing.
Pie facing.
You know, someone has to invent one. I don't know. Questions? So note the key point that every word in the input, every vector here gets an attention score, which is all learned. Everything is neural nets. And then it says how similar in some sense is each of these embeddings to the one I'm looking at currently, and then combine them together.
And in a way, it also mirrors the way you would probably do it. You know, like if you answer the question, you'd find where exactly is that.
The attention score says how similar is the embedding of this word to the embedding of this word here. This word in context, right? The state to that one. And it's telling you how relevant it is. As you're looking to translate, find the next word, you can imagine a long text. And the stuff that you heard many, many sentences ago is probably not relevant. And the next word is probably highly relevant. And the similarity in the embedding space tells you relevance. Note that sometimes things a while ago are relevant. Last night I watched Clinton. She gave a great speech. The she is going to be relevant to Clinton. And you need to know that languages differ. In some languages like English, you mostly give genders of people. Clinton, she, Clinton, he, Clinton, they are all different. In lots of other languages, you don't. So if you're translating from a gender-free language where there is no she, he, now you really need to figure to translate English, you got to find the gender of the pronoun. Was it Clinton? Was it someone else? Oh crap, and maybe that Clinton wasn't relevant because there's two Clintons. There's a he Clinton and a she Clinton. Maybe in fact you have to go farther and it said Secretary of State Clinton, which is definitely a she. So often you have to pay attention somewhere fairly far in the back to disambiguate, although mostly you pay attention to almost the most recent word.
But I mean, like, there's another side to attention scores as well, where we can say just like functionally here, what's the attention score doing? It's basically opening the floodgate. What are the things that we should let through? And both of them are there like at the same time. Like both of them are meaningful interpretations.
That makes sense. And the magic is that similarity of the embedding, the state embedding of this and the state embedding here, and there are a couple different kinds of similarities, but cosine is the easiest one, tells you something about relevance. And note that everything is neural nets all the way through, still trained by gradient descent.
But of course, the encoders are trained to make it so that the similarity matrix in encoding space approximates usefulness for answering the questions that we want to answer with it.
Sure, because we're doing gradient descent on predicting pi. And for pi, if you got to look the Untitled, if you're looking at that one, you're not going to get it.
Highly relevant.
And in fact, if you're really cool in a modern version, instead of words, we'll see next time people use word subword embeddings. So you might actually have on and tart, or tart is English tart, pi, and a, the past tense. So you might actually, in a modern version, instead of having words going in, you would have subword or byte codes, chunks of words, and you'd learn that the word tart is in fact tying to pi.
That's right.
This makes sense. This is sort of the key thing that goes away from the really local reinforcement, the RNNs that don't remember much about history. They can't remember a whole long document to something shorter. Cool. Now we could, instead of that, drop the sequence to sequence, take a sentence and actually put in some query. Ask a question like, who threw the pie? Or what was thrown? And now you could take an embedding of the question and I say, how similar is the embedding of my question, the query, we call it, the query or question, the query to each of the regions of the contextualized words in a whole long document. Make sense? And in general, who threw the pie is going to be most similar to, well, I got to be careful, it'll be similar to, the pie is similar to Untitled, but the who is to be similar to the he. And in a learn system, it now learns to say, given a query embedding, find the most similar part of, again, a long document. Think of a book, or at least a Wikipedia article. Find the most similar one, and then pull that out and learn, this embedding is the one that matters. Send that through a decoder and say that it was he threw it, which of course requires now to see more context. Who is the he? Which I don't get in the short sentence. But presumably there was some, Joseph or somebody through it. Does this make sense? Same idea, but not sequence to sequence, query to document. Good. Now one more final one. Oh no, we get cost first. Let's see, do I have the other one? Costs, how much these things cost. We need one more concept before we do this, which is self-attention. Which is like cool. So when you're actually training a transformer or a modern neural net, you can not only pay attention to an outside query for each word, but for each word in the document within a window, how similar is it to all the other words? Does that make sense? So instead of paying attention with an outside query to each word, for each word in the sentence, how similar is it to each other word in the sentence? how much attention should you pay? Now, what you'll find if, you know, when Clinton was visiting Iraq, she did X, the she will tie closely to Clinton, right? Because in fact, those pieces will be similar enough. And in terms of predicting future words, right, it's still self-trained. That's going to help. Does that make sense? That instead of a query in a document, you can make each word in the sentence, how similar is it to the other words? By the way, how does that scale with the length of the sentence? This is really obvious, but important point. I got a sentence of n words. How many self-similarities are there? Ballpark. N squared, okay? It's quadratic in the sequence length. So what does that mean if you're doing a transformer? If you have something, well, how big can you go reasonably? 10 squared, no problem. 100 squared, fine. 1,000 squared, okay. 10,000 squared, ixnay. Right, so how long can a transformer reasonably work? Order of magnitude, 1,000. I mostly use 628 is my standard BERT size, but now we're quibbling over details. But again, quadratic to have self-attention. Okay, so complexity of self-attention. Simultaneous, there's no history, right? It's not a recurrent neural net. We unroll it piece by piece. You look at everything at once, all pairwise connections. How much does it cost you? N squared for the sequence length times the embedding dimension from the static embedding. Or if you want, you could restrict it. And instead of doing the whole sequence at n, normally going to say, hey, I'll take 628 words or 1,000 words or something. And then I'm going to have something that's going to be typically 1,000 times n times d. So you can pay some cost again, but you get something that is now quadratic in the sequence length rather than quadratic in the embedding space, right? For the embedding of the word, the embedding of the image.
So I'm always confused how such a transformer net would say deal with the triple negation. By sentence, it's a lie if I tell you that it wouldn't be true that Conrad is not a professor.
Yeah, given that it's basically quadratic rather than the cubic and the pieces there.
It feels like it feels like there must be limitations, and of course there's ways of like maybe avoiding them through the learning of the exact embedding.
Well, I think the answer, first of all, is that humans are quite bad at doing things that have center embedding. The cat, the dog, ate, ran, killed. I can't even say it right because I can't actually do the embeddings. So people aren't very good at these either, is the first piece.
Yes.
Linguists say it's physically possible. The other piece I think is that I haven't tried those. When you get the triple negation, I didn't not want to see, well, in many languages, it's actually not triple negation. In English, technically it is for standard English. I think what happens is you got to think of each piece being embedded. So the attention then tells you these negations all relate pairwise to each other, but we've got a multi-layer neural net here. So as you go up the neural net, you're going to see in general what's going to happen is you'll get something that feels like a CNN. Although the transformer is global, its length n words in parallel, n squared connections, what's still going to happen is you might have a 10 or 12 deep neural net, very standard. And now what's going to happen is the first layer is going to have I didn't go, and it's going to embed that. And it's not true that I didn't go, will then get embedded there. And then I lied when I said that it's not true that I didn't go. That's going to get embedded. So I predicted layers 8 or 9, you'll start to see that pieces going together, right? So if in a linear world, you're guaranteed screwed. It won't work.
That's right.
But remember that all of these are done in moderately deep networks. We're talking sort of 6 to 12 layers typically. So that allows the triple negation. As you go each layer, you can get one more layer of negation in it. Cool. Fun. Questions? I mean, the self-attention was such a breakthrough in the transformer world. And I think it's not obvious. At least it wasn't obvious to me.
I found it very confusing when I first read it.
I did too. Okay, so again, why are people using transformers mostly rather than recurrent neural nets for language today? Takeaway? The answer's on the slide here somewhere. Sorry? Higher?
They can make it parallel.
Parallelism, right? The recurrent neural net means you've got to do n sequential operations going across things. The transformer is done in parallel. That's one other thing I did not say. The recurrent neural nets are self-supervised, predicting the next word. Transformers are mostly trained like an autoencoder. Take 10% of the words, blank them out, predict them. So instead of sequential, it says take words out of the middle of these n words, pick your 600 word image, your sequence, drop out 10% of them, right? And that's 6 words, and now predict the words in the middle from the other ones. And the self-attention helps do that because it says each of my removed words is best predicted by some of these 600 words. And in general, the ones that are physically close will make more difference, but not always. How long can word dependencies be? I went to the coffee shop last Tuesday with Conrad. We talked a bit. We discussed both coding languages and what we like to drink. And his favorite Java is actually, oh dear, that was a bad one. Which Java is it? His favorite coding language is not Java.
That's not
I
Java.
hope.
No. No, I can promise that it is not Java.
Okay, so note that it could be a long context, or it could be his favorite beverage is.
Yeah, and who is he?
Oh, and who
You
is
asked
he?
that question.
Is it the I or the Conrad, right? So note that there's some signal that goes back hundreds of words. If you're talking about Sumatra and Indonesia.
And in your example, yeah, like both what you mean with Java and what you mean with he is both
Right.
had long range dependencies.
Right. So the transformer really does help. It gives long range dependencies. It also means that when you go to generate models, like the sequence to sequence, you can predict, although you're predicting one word ahead, it predicts things that give you long sequences of reasonable predictions.
But one thing I find surprising now is that that computer vision now all of a sudden has transformers work so well.
Yes, computer vision is going to transformers.
It was never supposed to deal with these things.
CNNs, we know, we told you already, CNN's the right way to do vision. But I watch the vision guys getting more and more transformer.
Yeah, it's coming. Transformers eat everything.
This decade.
Yeah.
I know.
By the end of the decade, I'd say in 2 years will be the last continent.
I don't think so.
Okay, no. Look, there's a way where you can view transformers as a generalization of continents. One, namely, where instead with continents, we basically decide to use the same filter everywhere.
Right.
But why? Like, it kind of makes no sense to burn our compute on like doing local operations that are pointless.
The reason you do the assumption is you don't have enough training data to actually, is the top of an image and the bottom of the image typically the same? You go to Flickr or YouTube? No, the sky's usually up.
My PhD thesis, it's like fundamentally different. Like we put a camera on the head of a cat. The cat runs to the forest. We did then the statistical analysis of what's above the horizon and what's below. It's totally different. The spatial frequencies, the motion patterns, all kinds of things are different. So the idea of making the whole image convolutional, that embodies something that's wrong, namely that the world is the same all over the place.
Because it was cheaper, they didn't have the computer power to do it. Now we have more computer power. We can relax that assumption a bunch.
That's right. And in that sense, transformers might, as we go towards larger, more compute, transformers might end up eating the continents.
And what's the big difference between AlexNet, the classic CNN, and a transformer in terms of type of learning? What is AlexNet, the original CNN? What kind of learning is it? supervised with labels.
And we
What's-
can never get enough.
Never got enough labels, right? Even Google has enough labels. What's a transformer take? It's an autoencoder. It's self-supervised. It doesn't need the labels. The vision guys now, unlike 10 years ago, have the GPU power to actually run big unlabeled data sets.
Yeah, and what do? They take an image, they put holes into it, and then they ask their systems, tell me what happens in a hole. And it's
Exactly.
a very well-defined system. In fact, it's exactly equivalent to the way we train transformers. And that's why they move into the direction of transformers.
Right. Yeah.
So we use RNN to predict text as well.
RNNs are also used to predict text. Today, most of the commercial products like Google are transformers. There are plenty of specialized products using RNNs. So yeah.
So why does self-attention do much better than self-supervised? Because self-supervised does take the context and then use that to predict.
There's two different questions. One is self-supervised. So you can either be self-supervised by predicting the next word in a sequence as an RNN, or self-supervised like an autoencoder, like a transformer, predict missing words. Then that's one question. That's how the labels come. Predict next word, this missing word. The other question is self-attention, which actually is a different question. Self-attention says, I'm going to measure the similarity between each word and each other word in my n-word sequence. So I have n squared. For every word, I've got the similarity to all n minus one other words. Makes sense? Which works well with the missing word one. Because now I say, how much attention, what other words should be used to predict the missing one?
So if you're using, if you're just talking about prediction of next word, would self-attention and self-supervised have equal performance?
Would self-attention and self-supervised have equal performance predicting the next word? What did I say about the accuracy of transformers versus RNN so far today? No, did I ever mention accuracy?
You did not.
I didn't ever mention accuracy. I said transformers were better how? There are only two things that matter in computer science, right? Accuracy and speed. Transformers were better because they're faster. Why does that make them more accurate? Does it make them more accurate?
So everybody uses that faster than RNN.
And what do I get? Why do I care about the faster? How does that lead to more accuracy? You can give them more data. If I've got 500 billion words of English, I need something reasonably fast. You can easily burn through $100,000 worth of GPU time training a model. This is going to be hard for you guys to do at home on your, collab. They won't give you that.
You're like, so in 2019, you can burn through $10 million for training one model.
Well, the 10 million is the list price. If you look at the amount that Google's actually paying, it's not 10 million. That's how much I would pay if I were doing that much computing. If I were doing that much computing, I'd get a quantity discount. So those are little bogus numbers.
Let's see.
But we're quibbling over,
But hold on. I think there's another thing I want to say about the question. Like, one part of the question at some level is about the cost functions that we want to use. And our goal there is we have the data sets that we have, and we want to get as many bits of training data out of that as possible. And we only get so many labels, kind of labels like on the grand scale of things, the world just doesn't give us enough labels.
Right. Always expensive.
So therefore, if you want, like, as we go into the big data regime, kind of all the models switch to instead like predicting the data because you just don't have enough labels. The other one is about an architectural feature, which is self-attention. So those two are kind of orthogonal to one another. Like, we want to build good architectures, including self-attention and so forth. And we also want to have good cost functions. They're synergistic in that case.
And I think that is true. And it's slightly the case that the masking, dropping out 10% of the words, plays well with the architecture of self-attention, because the self-attention says, hey, great, predict this word. Note that it's also, unlike an RNN, which is left to right, more priority local things, the transformer is, here's a whole block, everything in the window is equally good. And that then requires a self-attention to get it to work really well.
Yeah.
Otherwise, you have to use a smaller CNN. So it's a question of how much do you assume locality of effect, right? The RNN says things exponentially in the past are exponentially unimportant. The transformer says everything in the window is equally important, or learn it. And if it's outside the window, I'm lost. I don't know about it.
Yeah, so for the transformers, it's actually hard to learn to be local. For the RNN, it's hard to learn to be not local.
Right. Make sense? Now, the nice thing is that the attention does eventually learn to be local. And one thing that they do in transformers is they put an index in. So each word in your 1,000-word sequence gets a number 1 to 1,000 or some sort of encoding of it. So they tell it actually something about sequence information.
And thereby they can learn it.
So they can learn it. Ungar.
There's a question by Ben who asked, so transformers still not work for time series data where you only have the past and not the future?
Well, transformers only work when you have the past and not the future. You can still use them in that case. And in fact, things like GPT-3 predicts the future only based on the past. It generates new pieces. So you can still train them. Usually you have past and future at training time. At runtime, you often only have the past. So it's very common that you have a sequence of words and use a transformer to predict what will be the next word, or a sequence of sounds for speech recognition, what will be the next word that comes out from it. But note the transformer embeds a bunch of frequency spectra across time into a piece there, and then you can use that to predict for a small supervision what will be the next letters that show up for those sounds. Make sense? Good question. Thank you, Dan.
Did you mention that attention does not have as much locality as RNN?
I did mention that attention does not have as much locality as RNN. RNNs, when you're making a prediction, all that matters is the current measurement and the output of the preceding layer. So it's got a Markov assumption, everything here. Attention, everything in the window contributes to everything in the window.
Okay, so the window becomes the
So the locality for the transformer is the window size. 10 years ago, that would have been hopeless because memory was too small. Now we can afford to do a reasonable window size. You can put in 600, 1,000 words, each with 300, 600 dimensional embedding. That all fits in memory now. So now you can afford to have a window size that's many sentences long and do the whole thing in parallel. So again, as a guy who's not an architecture guy, it astounds me how much of my machine learning stuff is driven by computer architecture.
Yeah, totally.
Which students ask, I'm an NLP guy, why do I have to learn architecture? I go, you don't have to unless you actually want to run any real data.
And say parts of the reasons why AlexNet was so popular is because they started taking hardware seriously.
Yeah.
So that's where their big jump in performance came from. They basically optimized everything, including the fact that they have 2 graphics cards.
Yeah.
I wanted to say one more
Yeah.
thing about this. You know,
Please.
like, if we have an RNN that steps through it, at any point of time, we have a summary of the past. That summary of the past in principle could be anything.
That
But
summary
of course-
could, but it's going to forget the distant past.
Under some assumptions, not like it could be a tap delay line where we have like up to some time.
Okay.
So-
good sheet.
So but basically, so even if there was an infinite amount in there, and it could in principle do that, we still have this inductive bias, which is that the gradients that we have there basically make it that everything that is really far will kind of see really weak gradients. So the training procedure very strongly biases RNNs to basically tell you something about the recent past. And the reason why we use LSTMs for a long time, where we used LSTMs here, is because that somewhat limits the effect.
Not as bad, but still not as good as transformers, because the transformers, everything is directly connected all the way through.
That's right. It's much easier to learn. The gradients look much better.
Yeah,
You can say, for the transformer, it will learn like stuff that's further away is less important. But it's not that it has kind of like to learn it in a very difficult way.
Yeah, there's no inductive bias. The inductive bias is different.
Yeah.
Cool. questions on these? So these are like, this is the core of contemporary NLP. The other thing to note is that you can actually do both at once. So you can also have a recurrent neural net underneath the hood for the representation, and then a transformer on top of it. And so you can mix and match these things. So I've tried to make them conceptually clean, but in practice, people often merge them together, where you have a transformer style connection with an underlying recurrent neural net model. You don't have to pick one or the other. Cool. Okay, so yeah, one more. So another thing that's popular these days is to ask a question. So here's an image as an input, and the question is, what are sitting in the basket on a bicycle? That's a weird question, but that's the question I stole. How would you go about answering, building a computer model to answer questions about images like this? What is that?
What?
I thought it might be a goat or something fun, but no.
It's two dogs.
It's two dogs. The answer seems to be two dogs. Conrad has got the answer.
And what? I only see two dogs. It's
two dogs. Two dogs. I think. Okay, but the question is not what the answer is. The question is what architecture do you set up your deep learning model to answer this question?
What do you think you do when you solve that problem? Now, we had some trouble, but like, what happened?
So on a CNN and an RNN, I want something on the image, which will be CNN-like in the current architecture, although maybe not next year, and an RNN or a transformer on the language. So I got two inputs, an image. Now what else do I need? Especially picture a bigger image, but even a small one.
And I want to push you on this, like, what did you do?
Yeah.
Because I think that's something very important. What did you first do? Look at the picture or read the text? Read the text.
So you started with the text, you embedded the text with some information there maybe.
Okay, then I kind of know there must be a bicycle with a basket on top of it and something sitting on it, which kind of has my big question mark on it. And an embedding of kind of broadly that visual question. And then what did you do?
We have an Untitled Chapter from Dan again. You need something to connect the text to the image. I say that the picture of a dog is spelled dog.
So I need to connect the text to an image. The picture of a dog is spelled dog. So half of that is correct. So you want an embedding of the language to match the embedding of the image. But do I want to embed all of the language and all of the image? I could take the whole image and use the penultimate layer of an autoencoder or something, and I have a 1,000-dimensional image embedding.
Yeah, there's also a red bike.
There is a red bike.
Yeah, shouldn't we be looking at how would we embed the red bike? That's a trick question.
Here's a hint. What have we been talking about the last half hour? What's the one-word summary of the last half hour?
It wasn't ConvNets.
Wasn't even transformers. Attention.
Attention.
Right? So as you look at the image, and people do this eye tracking, it's great. They can actually monitor, and when you read this question, you will see people first looking at the bicycle, then looking at the basket, then looking above, then their eyes will bounce back and forth at the dogs there. People will attend to it. You can't actually take in a large image all at once. I can't see this whole room without scanning across it. So you actually will shift apart them. So typical sort of model, take in a question, do some sort of a CNN or LSTM or something that does embeddings of the query, take in the image, do some sort of CNN, but note that maybe within the different image, there are different pieces, depending upon where you're looking in the image. Now you want to match different pieces of the query. like the what and the sitting and the basket and the bicycle, to different pieces of the image, right? So bicycle embedding should match, well, this one and that one. Basket should match that one. Basket on bicycle is sort of this one. And the what is going to have to match something that's sitting, although sitting isn't quite there. It's going to be contextual, but somehow the point is that for a large query and even a moderate sized image, one wants attention both over the words and attention over the image. Not all of the image is relevant to the question. To try and take a whole image and capture it in a single vector misses too much of the information. There's too much going on. If I asked you what's to the left of the basket on the bicycle, then I would see the red bicycle, right?
That's right.
What's behind the bicycle? I don't know. Looks like a chalkboard almost. A
Yeah,
window.
this
It's a
must
window.
have been taken in this room.
It's a window. Okay, hard to tell, but note this fact that attention, well, first note that lots of stuff, we'll talk about this more next week, lots of things are now multimodal. You have images and text, or sound and images, and note that you need attention typically on the images and on the questions. In the old days, oh, like the stuff we covered 3 weeks ago, there was these really funny notion that every picture is a picture of one thing. There's a picture of a dog, or a picture of Conrad, or a picture of a piece of chalk, and you say, what is it? That's nice, but that's not reality. Reality is there's Conrad and a piece of chalk and lots of other things, right? And if you look at how people or computers look, the people sequentially, eyes bounce around. You look back and forth from me to Conrad, you look over there, right? You'll be focusing on different pieces, and depending upon the prompt, the query, the question, when I say chalk, it's going to tend to make you focus over here more. Make sense? And computers are subject to the same sort of computational limits that we are. Abstractly, we can quibble over the details. Conrad's not going to argue too much. Therefore, it needs to answer a query to look across the image and find the little pieces and try and say, where in the image, what am I looking for, match it together. And how to do this, very hot right now. Lots of people doing different models.
I also want to just, like there's something very abstracted in the top layer, no? Like feature vectors of different parts of the image. There's like a lot of magic happening in this little arrow coming out of the CN into it. You know, like, what does that mean? Like, ideally, we'd like object-based attention, which people have. I can look at you or look at you, and in a way, like, my world is only covered by you at that point of time. And in a way, we do that in a very ugly way still to this day. Yeah. And in a way, it should go back, not like it should go back to the left, where it can say, show me the basket. It's almost like I want like go all the way to the pixels. Like what's the parts of the basket?
Yeah.
To answer good questions about the basket.
And I think the bottom line, I picked this because this is a state-of-the-art paper by a team including Alex Mola, who I respect. The current state of the art is we're working on figuring out how to do this structure and this attention. So what Conrad wants is things that will be showing up in the next couple of years in this community. But it's still fairly primitive in the sense of not really having hierarchical structure, of not having prior knowledge about objects, of not being bidirectional, right? Where, in fact, you go back and forth between the language and the image, right? You reinterpret they're great psychology experiments where you say, you know, look at the frog on the napkin, and as you see the picture, you reinterpret. Is there one frog? Are there two frogs? Oh, the frog on the napkin, not the frog that's on the plate. So, yeah. So in real human experiments, what people show is that the images change how you understand ambiguous language, and the other way around. We don't quite have that flexibility in the current architectures. They're pretty primitive, I think.
I should mention maybe here some of the things that my lab are about object-based attention. Yeah. So that's why I find it interesting. One of the reasons why I find it interesting.
Cool. That ends the attention piece. I thought we might talk a little bit about a societal version, or do you want to do something else?
No, let's do the societal version. That's very important.
Okay, so I'm unfortunately a meta reviewer for ethics for ACL.
Oh, wonderful.
Computational
Congratulations.
Yeah, and consolations, as we say. So they sent me a couple papers. I'm reading one last night. I figured you guys would help me with this. So I get a paper and two of the reviewers flag the paper. It's a paper that takes a bunch of questions for measuring personality, extroversion, introversion, conscientious, less conscientious, open to experience, more closed. And it builds some language models based on the questions, and then takes a bunch of people's Twitter data where the people have answered questionnaires and it predicts their personality.
That's awesome.
Sounds sort of cool, sort of thing I do a lot. So a couple of the reviewers said, oh, this seems dubious ethically.
Yeah, I think I'm with them.
So what should I be checking for, first of all? Not you first, them, then you can tell me. What should I be checking for in terms of ethics here? This is a journal publication, a conference publication, but
Yeah. What would we be worried about that?
why are they worried? Why are people wasting my time asking me these
The
questions?
code's gonna be on GitHub. Is that gonna be a problem?
Code will be on GitHub. Yeah,
What's it going to label people as? Is it going to like give someone an insulting label?
well, there are 5 labels because there are 5 factors of personality, and it will give a number for each one, and the labels are designed in theory by psychologists not to be insulting. So extroverts and introverts, although Americans tend to be sort of pro-extrovert, in general, the belief is that it's not really better to be extrovert than introvert.
On conscientiousness, though, there might be like
Yeah,
some-
and agreeable, disagreeable. Would you rather be agreeable or disagreeable?
I take the disagreeable slot.
Well, in fact, there's something to be said for being disagreeable because it means you're not as subject to societal pressures. So you can stand up better against peer pressure. Well, that's one concern, but they're not going to release the names of the people. It could be skewed, so it's who knows the data came from. So it's certainly not representative. I don't know where the data came from. So you might worry that it's misleading in the sense that it's some pieces. Not enough to reject it. Yep.
If the labels are accurate.
So who knows the labels are accurate, but that's a quality concern rather than ethics concern. I might worry about it.
It could be, such a model could be used to introduce biases against people. So, I mean, you could try and predict the person's.
So it could be used for evil in some sense. There was a great case, not evil, maybe, well, who knows ethics? I can tell you that what happened. There's a company called Admiral Insurance Company in England. By the way, the cultures are very different. China, England, the US, even US and England are quite different. They introduced a great product. They said, we sell car insurance. Share your Facebook with us if you wish. We will entirely privately analyze it. And based on that, we'll decide whether you're worthy of a good driving bonus. They probably check for conscientiousness.
Probably.
And they launched this product purely opt-in. They will not sell or share your Facebook with anybody. All they do is run it through an NLP algorithm like this paper was doing. And if you're eligible for a discount, they give it to you. Good product, bad product.
Evil product?
I think evil's a different question. I'm asking a pure business question at the moment.
Good.
Evil is another question.
But it would work. It would describe some proportion.
Oh, it
of
was
the
accurate.
errors.
So the question was not the accuracy. We're talking about the societal. The F1 accuracy was great. That wasn't the problem. The product lasted. Good product? No? Pardon?
I think you don't need somebody's Facebook profile to decide whether they should be.
You don't need your Facebook profile, but it helps to know how conscientious. Do you spell things correctly? Are you sloppy about your spelling? Are you texting as if you were drunk, posting as if you're drunk posting? Yep. If you're a careful person who actually tends to not drunk post at 3 in the morning, you're a careful person who's less likely to drive drunk at 3 in the morning. This is empirically true.
Yeah, I believe it.
There was no problem with this. The machine learning was fine with this product. The problem was a societal issue, which I don't think it would have been a problem in the US.
But I think I would predict, basically, can there be any group? Like, no, we just heard about the product. Could we imagine that there's a group that the system appears to be discriminating against or is discriminating against?
Could be. That was not actually why what happened is it lasted three.
But I guess that it's also the case.
That's probably the case, which they didn't even worry about. Yes, they could well have. In fact, this is in England, like the US, England has a lot of people who speak English as a second language.
Uh-huh.
And right, former empire. And their language will look really different. Oh, it might have more spelling errors, even
Possibly.
though they may not be less conscientious.
So they would have discriminated against me.
For example, I once ran
That's not cool.
a correlation of IQ test with Facebook language. And I found a whole bunch of people in California who had scored low on the IQ test. I was wondering what's going on. I thought, oh, okay, I'm from California. I know that there are lots of Mexican Americans, but no, I was wrong. It turns out there are a lot of Filipinos and they speak Tagalog. And are they dumber than Americans? Filipinos on average?
That sounds extremely unlikely.
Seems unlikely, but are they scoring less well on English language IQ tests than native speakers of English?
Yeah, me too.
You too, yes! In fact, it turns out that Tagalog speakers in California, in my non-random sample, score much worse on English language IQ tests than people who speak English as a first language. Oops. Anyway, popping back to England.
Okay, but hold on.
Yeah.
Now I want to know the story. Like they rolled that thing out, and
They rolled the thing
there
out.
are groups
It
like
lasted
this.
3 days before the flack that they got was enough that they said, oh, on second thought, we messed up. We apologize. We're not going to offer this product anymore. People viewed it as being too creepy, even though it was opt-in, private, safe, and nobody complained about discrimination in England 3 years ago.
Yeah, there must have been discrimination.
There must have been discrimination, but that wasn't why they were forced to take it back.
Yeah.
So
What's next?
no, we still haven't answered this question because there is in fact one other big reason, which
An
is
extra ethical.
the real ethical issue that most reviewers are concerned with. What's the first thing I should check for? I would check for, and I did check for in the paper. If you do a paper where you're publishing a paper in, say, natural language processing about people or images about people, what do I look to see whether they have? Sorry?
Inclusiveness, trying to.
Inclusiveness is nice, but that's not the first thing that's the obvious checklist. Yeah.
Then just the data privacy.
Data privacy would be one issue, which is getting closer to it. Yeah.
Or I suggest consent of users.
Consented users would be a good thing. It turns out that the users did consent. I checked out to see the original thing, but the people who did the paper weren't actually doing the research. They got someone else's data. What's the process? These are actually a German group, but in the US and most of the world, if you write a paper, whose job is it to check as a front line to see whether this is ethical?
That's important to know.
That's important to know. And the authors of this paper did not do this. So they didn't
Which
know.
is unfortunately very common for computer scientists.
Psychology,
who lack
medicine,
that training.
everyone does this in computer science. People don't think about it.
And
but
what
they're-
is it? What is it?
The Institutional Review Board. All major universities and increasingly major companies have some organization in America, in the universities called the Institutional Review Board. Their job is to check both ethics and data privacy and data security, and in particularly informed consent. Did you actually explain to the people what you're going to do with their data? Did you tell them you would keep it forever, or share it with everybody, or share it only with researchers, or sell it or not sell it? So informed consent and an institutional review board had this paper actually checked with their institutional review board and signed off, I would have immediately said, of course, publish it. Some professional has reviewed it, but they didn't. They said, we don't need to because we're only using someone else's data. Is it okay always to use someone else's data? They didn't collect any data. It was someone else's data they used. Is that
There's a
ethical?
lot of computer scientists that do that.
Of course, I
Even
didn't touch the
ImageNet.
data.
Not like ImageNet contains people's faces.
Was there informed consent?
Of course, there's never been informed consent.
You mean these people are using a bunch of images of people without asking the people?
There could be your face in it for all that I know about
It
it.
could well be. My face is on the web without a
Yes.
mask, you know.
That's right. And they scrape your data. That's how ImageNet was made.
I do know that. There's a couple of companies that are scraping my data in violation of Facebook and Twitter's terms of service and using them to sell products to the police. So I think the big takeaway from this piece is if you're doing anything that involves collecting data about people, like their personality or their Twitter or their Facebook or their images, you might want to check with someone else who does this thing for a living and say, hey guys, is there any problem? In this particular case, I think the IRB, as we call it, would have approved it. But since they didn't check, now, unfortunately, I am now serving as their IRB.
But it used to be that computer scientists would never do that.
Never.
And now we start being
Never.
more aware because it's people's data. They have a right to that.
But this is the first year that we actually have a full formal review, ethics review process all the way in place for the natural language conferences.
Poor authors.
So it's a bummer. Welcome to the new world.
Yeah.
Cool. What time should we end?
We can end now-ish, unless you have stuff.
This is really the piece that I wanted to point out. It's just that when you collect data, think about whose data and did they give you permission. If you download a bunch of gay and straight faces from the web and someone else shares it with you, it doesn't necessarily mean that people be chill about their sexual preferences being made public.
Well, in this case, their character.
Or in this case, their character.
But Lyle, I wonder why you ended there. So you can say there's also risk of harm here. Now, like if you can from a photograph know my character, you can exploit me even more. And like
so I think in this case, if they were resharing the Twitter data, that would be a different issue. So one thing I've had, so I've scraped lots of web data. The IRB here says, oh, Lyle, you've scraped these public fora for people where all the data is publicly available, and then you collapse it and analyze it and then publish the results. You can't do that because if you share the data, someone can go back and figure out even the summarized public data has information on it.
Yeah.
And so in this particular case, the data was not going to be released at all. They weren't going to share it at all. It's under lock and key. And the results they're publishing are abstract, so there's no data leakage. So that was actually clean, but you worry about it, right? Can I collect your tweets and republish them, even though they're publicly available? Well, first of all, Twitter's terms of service has some limitations on resharing tweets. So it's a legal question, but note that even publicly available data, when reshared in the right condensed format, can actually be potentially damaging.
That's right.
So this particular paper wasn't going to reshare the data, so I wasn't worried about it.
Right.
Awesome. We're at time. We're still talking to people about projects. We're still happy to meet with you. Full speed ahead. And we'll do more NLP next week. It'll be fun. Cool.